Section 3, Elements of Design. In this section, we're going to be covering sight distance and vertical alignments. You can find information about this in the EPG Category 200 on Geometrics, 230 Alignments of Roadways, and 230.2 Vertical Alignment. It can also be found in the AASHTO 2018 Green Book, Chapter 3. Before we get into sight distance, we're going to talk about precision for plan dimensions. Precision for dimensions used in the preparation of plans is shown in the EPG table 237.1.1. Many of these settings will utilize throughout this section. Definition of sight distance. Sight distance is the length of roadway ahead that is visible to the driver. Sight distance is an element of design that affects the safe and efficient operation of the roadway, and it's given careful consideration during the location study and preparation of the preliminary plan. There are four aspects of sight distance discussed in the AASHTO 2018 Green Book, Chapter 3. The first one is stopping sight distance. This is the sight distance needed for stopping, which is applicable on all roads and streets. Number two is the passing sight distance. This is the sight distance needed for the passing of overtaking vehicles, applicable on only two-lane highways. Third is the decision sight distance. The sight distance needed for decisions at complex locations. And the last aspect is the criteria for measuring these sight distances used in design. The definition of stopping sight distance is based on the anticipated posted speed and is the sum of the distance for the braking reaction and the braking distance required for a driver to stop the vehicle after sighting an object on the roadway. The first is the brake reaction distance. This is the distance traversed by the vehicle during the time the driver takes to react. The second is the braking distance. This is the distance needed to stop the vehicle. The AASHTO 2018 Green Book Section 3.2.2 provides a couple of tables for stopping sight distance. On the left is the stopping sight distance for level roadways. On the right is the distance when you have a grade, whether it's downgrades or upgrades. You'll notice that downgrades have a longer distance. Decision sight distance is used when stopping sight distance is just not adequate to allow a reasonable, competent driver the distance to react to a potentially hazardous situation. If a situation that requires decision sight distance arises, consult the AASHTO Green Book. Drivers need decision sight distance whenever there is a likelihood for an error in either information reception, decision making, or control actions. Examples of critical locations where these kinds of errors are likely to occur and where it is desirable to provide decision sight distance include interchanges and intersection locations where unusual or unexpected maneuvers are needed, changes in cross sections such as toll plazas and lane drops, in areas of concentrated demand where there is apt to be visual noise from competing sources of information, such as roadway elements, traffic control devices, and advertising signs. The 2018 Green Book, Section 3.2.3, has a table 3-3 on decision sight distances. In that table, there are several different avoidance maneuvers, A through E. Each one is listed on what type of maneuver it is and the amount of time for each maneuver. Passing sight distance. Passing sight distance is only a consideration for undivided highways. It is not practical nor desirable to design crest vertical curves based on passing sight distance because of the excessive length of the curve that the curves would require. So how do we get adequate passing sight distance? To attain adequate passing sight distance and still keep the length of curves to an acceptable length, vertical curves should be designed based on appropriate grades for the design speed and terrain. However, if passing sight distance needs to be calculated to determine the no passing zone striping, the AASHTO Green Book has formulas and tables to determine the design passing sight distance, and that can be located in Chapter 3. In the AASHTO 2018 Green Book, page 3-11, and the NCHRP Report 605 talks about the minimum passing sight distance and the assumptions that go along with it for calculating minimum passing sight distance. The first assumption is the speeds of the passing and opposing vehicles are equal and represent the design speed of the highway. Assumption number 2 is the passed vehicle travels at a uniform speed, and the speed difference between the passing and passed vehicle is 12 miles per hour. 3. The passing vehicle has sufficient acceleration capacity to reach the specified speed difference relative to the passed vehicle by the time it reaches the critical position, which generally occurs about 40% of the way through the passing maneuver. 4. The lengths of the passing and passed vehicles are 19 feet, as shown for the P design vehicle in the AASHTO section 2.8.1. 5. The passing driver's perception reaction time in deciding to abort the passing vehicle is 1 second. If the passing maneuver is aborted, the passing vehicle will then use a deceleration rate of 11.2 feet per second squared, the same deceleration rate used in the stopping sight distance design criteria. 7. For a completed or aborted pass, the space headway between the passing and passed vehicles is 1 second. And lastly, the minimum clearance between the passing and opposing vehicles at the point which the passing vehicle returns to its normal lane is 1 second. AASHTO 2018 Green Book states the minimum passing sight distance for use in a design are based on the minimum sight distances presented in the MUTCD as warrants for no passing zones on 2-lane highways. The figure that you see here is in the MUTCD manual. In the AASHTO 2018 Green Book, page 3-11, there's a table 3-4, passing sight distance for design of 2-lane highways. In that chart, you'll have a design speed, the speed of the passed vehicle, the speed of the passing vehicle, and the overall distance for the passing sight distance, which matches the MUTCD manual's table. Passing sections shorter than 400 to 800 feet have been found to contribute little to the improving of traffic operational efficiency of a 2-lane highway. In determining the percentage of roadway length with greater than minimum passing sight distance, the passing sections shorter than the minimum lengths shown in Table 3-5 should be excluded from consideration. Now we're going to talk about the frequency of passing sections. It is not practical to directly specify the frequency of passing sight distance areas. The designer should provide passing sight distances based on topography of the terrain, design speed, cost, and spacing of entrances. Passing lanes and 2+1 roadways. In some situations, it may be more practical to provide a dedicated passing opportunities by adding a climbing/passing lane. For more complex situations, a designer should consider a 2+1 roadway. These facilities provide a continuous third lane to offer alternating passing opportunities to either direction of travel. Contact the Engineering Policy Group for policy guidance. Sight distance is the distance along a roadway throughout which an object of a specified height is continuously visible to the driver. This distance is dependent on the height of the driver's eye above the road surface, the specified object height above the road surface, the height and lateral position of the sight obstruction within the driver's line of sight. Height of the driver's eye for all sight distance calculations for passenger vehicles, the height of the driver's eye is considered to be 3.5 feet above the road surface. Height of the object for stopping sight distance and decision sight distance calculations, the height of the object is considered to be 2 feet above the road surface. For passing sight distance calculations, the height of the object is considered to be 3.5 feet above the road surface. Sight distances should be considered in the preliminary stages of design when both the horizontal and vertical alignments are still subject to adjustment. Stopping sight distance can easily be determined where plan, profile, and surface information can be drawn using computer-aided design and drafting systems, or otherwise known as CAD. The straight line of sight from the driver's eye position to an object on the road must be clear of obstructions. Stopping sight distance for general use in design of horizontal curves, the sight line is the chord of the curve, and the stopping sight distance is measured along the center line of the inside lane around the curve. The values of horizontal sight line offset, or HSO, are determined by setting S, as shown in figure 313, and in equation 337, equal to the stopping sight distance, SSD. Next, we have an example of horizontal sight distance. In this example, we're going to try to calculate the radius of the highway center line. In this example, we have a design speed of 70 miles per hour. Our HSO is 25 feet. That is the offset from the obstruction to the center line inside lane. We also have flat grades and a lane width of 12 feet. First thing we're going to do is try to calculate what is the stopping sight distance. So we're going to utilize AASHTO Table 3-1 stopping sight distances on level roadways. Again, our design speed is 70, so if we highlight the 70 row and go all the way over to the right, you can see that our stopping sight distance is going to be 730 feet. Next, using the chart in AASHTO, figure 314, we're going to go ahead and start plotting on the chart our design speed, which is 70. Next thing we're going to plot is our offset of 25 feet. And if we then draw a horizontal line from that intersection, we'll get our radius of 1,170 feet. Now that's the radius to the center line inside lane, not the center line of our alignment. To calculate Next, we're going to calculate the radius of the curve. We're going to utilize the radius of the center line inside lane, which is 1,170 feet. We're also going to take half of the lane width, which is 12 foot, and we're going to add it to the radius of the center line inside lane. And when you do that, you get a value of 1,176 feet. Next, we're going to try to show you why it's not practical to design with passing sight distance versus stopping sight distance. The minimum passing sight distance for a two-lane road is about twice the minimum stopping sight distance at the same design speed. We've got the three charts down here. The first two deal with stopping sight distance. The first one's on level roadways, the second's on grades, and then the last chart is the passing sight distance chart, table 3-4. If we look at a certain design speed, say 70 miles per hour, if you look at the distances, you'll notice that the passing sight distance is much longer. So therefore, we design with stopping sight distances in almost all cases. Next, we're going to start talking about vertical alignments. This can be located, or information about this can be located in the EPG category 230.2 and also in the AASHTO 2018 Green Book section 3.4. Vertical alignment is a series of straight profile lines connected by vertical parabolic curves and is referred to as a profile grade line, or PGL. There are two types of vertical curves. We have crest curves, and the design of crest curves is concerned with seeing over the hill far enough to permit a emergency stop. With sag curves, the design of a sag curve is concerned with the headlight illumination across the valley far enough to permit an emergency stop. Design for both is typically controlled by stopping sight distance. On occasion, decision sight distance may be needed. Vertical curves should result in a design that is safe, comfortable in operation, pleasing in appearance, and provide adequate drainage. Why are vertical alignments important? Vertical alignments help in the calculation of amounts of cut and fill. The profile grade line is the key factor in proper drainage. In rock or in flood areas, the PGL should be higher than the existing ground. The PGL sets the smoothest for the roadway. Drivers should feel comfortable when riding the roadway. How do we determine a vertical alignment? A vertical alignment is applied at the design element, and you're trying to balance the hills and valleys so that the beginning earthwork is close to balancing out. Please note, though, that even though the vertical alignment is well balanced, your earthwork may not be. Individual cross sections are used to accurately balance earthwork. Next, we're going to talk about some points about grades and vertical curves. Grades play a greater influence on trucks than passenger cars. Studies show that trucks increase in speed by about 5% on downgrades and decrease in speed up to 7% on upgrades. Studies show that regardless of the average speed on the highway, the more a vehicle deviates from the average speed, the greater its chances of becoming involved in a crash. In recreational routes where low percentage of trucks does not warrant a climbing lane, designers should consider adding an additional lane. AASHTO recommendations on control of grades for design. Maximum grades of 5% are considered for 70 mile per hour design speeds. Minimum grades of 0.5% is typically used, or in some cases 0.3% for outer edge of roadways. Refer to the AASHTO Drainage Manual for more information on drainage considerations. Profile grade lines, or PGLs, on floodplains must keep shoulders at a minimum 1 foot above the design high water. That's found in EPG 230.2.11. Maximum design criteria on grades. The chart below summarizes the AASHTO Green Book guidelines for selecting a max rate of grade. For minor roads, local rural roads, local urban roads, and special purpose roads can be found in Chapter 5. Rural and urban collectors are in Chapter 6. For major roads, rural arterials, urban arterials are in Chapter 7. And then rural freeways and urban freeways is in Chapter 8. In AASHTO 2018 Green Book Figure 3-4, we can see the 4 types of curves that we have. The types on the top, Type 1 and Type 2, are crest curves, and Type 3 and Type 4 are sag type curves. Next, we have a document on the vertical curve and the equations on how to calculate critical points of the curve. First, we have a VPC, which is the vertical point of curvature. The VPI is in the middle. It's the vertical point of intersection. And then we have the VPT, which is the vertical point of tangency. The distance between the VPC and the VPT is L. The distance from the VPI down to the vertical curve is E, and the distance from the vertical curve at the VPI location down to the chord is M, which also equals E. We have 2 grades, the grade coming into the curve, which is G1, and the grade going out of the curve from the VPI to the VPT is grade 2. These equations over on the left we'll be using throughout the next couple slides. Next, we have an example of a vertical alignment geometry. In this example, we have a 600-foot vertical curve connects a positive 4% grade to a negative 2% grade at station 25 plus 60.55 and an elevation of 648.64 feet. The example wants us to calculate the location and elevation of the VPC, the middle of the curve, the VPT, and the curve elevation at station 24 plus 00. We're first going to calculate the location and elevation of the VPC and the VPT. To do that, we're going to look at the VPI. The VPI is in the middle of the VPC and VPT. So what we need to do is take the curve length and divide by 2 to calculate the station values down to the VPC and up to the VPT. When we do that, we get the following values for the VPC of 22 plus 60.55 and the VPT of 28 plus 60.55. Now we're going to calculate the elevation. To do that, we're going to take the elevation of the VPI and we're going to go the distance, half the curve length of 300 feet, and times it by each grade. So to get the elevation of the VPC, we're going to use the minus 4% grade times 300, and we're going to add that to the VPI elevation. When we do that, you'll see that we get a elevation of 636.64 for the VPC elevation. To do the VPT elevation, we're going to take the 2% grade, the minus 2% grade, and do the same thing, times it by 300, and then add it to the VPI elevation. So when we do that, we get 642.64 feet for the elevation of the VPT. Next, we're going to calculate the location and elevation of the middle of the curve. Well, we know the location already of the middle of the curve. It's the VPI station. But what we don't know is the distance from the VPI down to the curve itself, which is an E distance. This E distance equation is found on the sheet of equations that we showed earlier. The E distance from that sheet equals A times L over 800. A equals G2 minus G1. When we plug in the values, you get the following, and we get an E distance of negative 4.5 feet. To calculate that elevation, we just simply have to take the VPI elevation and minus the E distance. When we do that, we get an elevation of 644.14. The next thing we're going to do is we're going to calculate the curve elevation at station 24 plus naught. Station 24 is at this location. It's some X distance up from the VPC location. The X value is simple to calculate. It's just 24 plus 00 minus the PC or the VPC station value. We get an X value of 139.45 feet. To calculate that elevation, we've got to calculate this Y value. Again, this Y value is on the previous slide with all the equations on it. Y equals 4E times X divided by L squared. When we plug in the values, we get the following, and we get a value for Y of negative 0.97 feet. Now to calculate the elevation at station 24 plus 00, we take the VPC elevation and we add in G1 over 100 times X plus the Y value. When we do that, we get the following values and we get the following elevation. The elevation at 24 plus naught is 641.24 feet. Lastly, we're going to try to locate the high point and its elevation. We're guessing where that high point is. It's somewhere in this location here, and we're going to call that an X high point or low point value. To calculate that X high point or low point, we use the following equation from the previous page. You plug in the values, and we get a value of 400 feet from the VPC to the high point. Next, we're going to calculate the elevation. Next, we're going to calculate the station, which is very simple. You just take the VPC value plus that X value of 400 feet. We get a station value of 26 plus 60.55 for the high point station. Now we're going to calculate the elevation of that high point. To do that, you'll use the following equation. That Y value that we're going to be using in that equation is from the G1 tangent, grade 1 tangent, and not the G2 tangent. So that's the only trick you have to remember when using this equation, is that the Y value is from the grade 1 tangent line. So we got to calculate Y. Y again equals the following equation. If we plug in the numbers, we get a value of negative 8 foot for Y. When we plug in the rest of the values, we get the following. And for a high point elevation, we get 644.64. Vertical curve general considerations. Vertical curves should be simple in application and should result in a design that enables the driver to see the road ahead, enhance vehicle control, is pleasing in appearance, and is adequate for drainage. Research has shown that vertical curves with limited sight distance do not necessarily experience frequent crashes. It is recommended that all vertical curves be designed to provide at least stopping sight distance shown in AASHTO 2018 Green Book Table 3-1. Some more vertical curve general considerations are: for driver control, the rate of change of grade should be kept within a tolerable limit. Appearance should also be considered in designing vertical curves. A long curve has a more pleasing appearance than a short one. For simplicity, a parabolic curve with an equivalent vertical axis centered on the vertical point of intersection, the VPI, is usually used in roadway profile design. Minimum lengths of crest vertical curves are expressed as about 3 times the design speed in miles per hour. Lmin equals 3 times the design speed. MoDOT EPG 230.2.5 states the following: where practical, vertical curves at least 300 feet in length should be used. For the minimum passing sight distance shown previously in Table 3-4 on a previous slide, the minimum length of crest vertical curves are substantially longer than those for stopping sight distances. Generally, it's impractical to design a crest vertical curves that provide passing sight distance because of the high cost where crest cuts are involved and the difficulty of fitting the resulting long vertical curves to the terrain, particularly for high-speed roads. Passing sight distances on crest vertical curves may be practical on roads with unusual combinations of low design speeds and gentle grades, or high design speeds with very small algebraic differences in grades. Ordinarily, passing sight distance is provided only at locations where combinations of alignment and profile do not need significant grading. When the height of eye and the height of object are both 3.5 feet, as used for passing sight distance, use the following equations. Minimum lengths of crest vertical curves based on sight distance criteria generally are satisfactory from the standpoint of safety, comfort, and appearance. An exception may be at decision areas such as ramp exit gores, where longer sight distances and therefore longer vertical curves should be provided. For further information, refer to AASHTO's 2018 Green Book section 3.2.3, Decision Sight Distance. When the height of eye and the height of object are 3.5 feet and 2 foot respectively, as used for stopping sight distance, you should use the following equations. There are 2 potential geometric conditions. First, you can have S being shorter than L, or less than, or S being greater than L. The same geometric conditions are also true for sag curves. Each geometric condition has its own set of equations. Each solution, whether S is less than L or S is greater than L, can be a valid solution. Rate of vertical curve K is the length of the curve per percent algebraic difference in the intersecting grades, called A. K equals the length of curve divided by the absolute value of A. A equals G2 minus G1. G1 is the grade of the initial tangent in percent. G2 is the grade of the final tangent in percent. If you rearrange the equation, you can get the following. L, length of curve, equals K times the absolute value of A, or the absolute value of A equals L divided by K. Table 3-1, stopping sight distance on level roadways. What this chart will give you is an interaction between the design speed, the algebraic difference, and the length of crest vertical curve. For example, if you had a 70 mile per hour design speed and you wanted to create a vertical curve length equal to the sight distance, you would carry that 70 mile per hour line down to the dash line like we have here. You'd go straight down to calculate your length of curve, and then you would go over to the left to calculate your algebraic difference, or not calculate, but pull the value off the chart. Now, a lot of times you know your algebraic difference in grades before you know your length, and you also know your design speed typically up front. So if you know your algebraic grade and your design speed, you can calculate an appropriate length of curve. For example, if I have again a 70 mile per hour design speed, and say this time we have a 4% algebraic difference in grade, we come to a intersection point there, and if you go straight down from that point, you can calculate the appropriate length of crest vertical curve. Now we're going to go into another example, crest vertical curve calculation. For a 2-lane highway with a design speed of 50 miles per hour, determine the minimum length of crest vertical curve with G1 equal to 2.5 and G2 equal to a negative 1%. Design the length of curve L such that it provides enough actual sight distance S. Assume that the curve will be based on stopping sight distance. So here's our grade 1 going in to the vertical, or at the beginning of the vertical curve, and negative 1 going out of the curve. In this case, we have a crest curve. So again, this curve would be classified as a crest curve based on the grades of the curve. The design of the crest curve is concerned with seeing over the hill far enough to permit an emergency stop. Choose L to provide S sight distance S greater than the stopping sight distance. L equals length of curve, S equals sight distance, and SSD equals stopping sight distance. When calculating stopping sight distance, utilize the steepest grade. In this example, the 2.5% grade is the steepest grade in a two-way traffic, and a negative 2.5% grade will be used to determine the stopping sight distance. So let's calculate the stopping sight distance, and to do that we're going to use the AASHTO table 3-2 stopping sight distances on grade. Since there is no 2.5% downgrade slope, we're going to use the next conservative value of 3%. So we highlight the 3% downgrade slope, and the reason we use downgrade over upgrade is because typically a downgrade will give you a more severe or longer stopping sight distance. So when we use the 50 mile per hour row, we get a stopping sight distance of 446 feet. Now, before we calculate the length of curve, we're going to go over the minimum length of crest vertical curve as expressed as about 3 times the design speed in miles per hour. So the equation would read L min equals 3 times the design speed. And when we plug in the numbers, we get 150 foot for our length of curve, which is our minimum length of curve. So when we calculate our length of curve, it has to be greater than 150 foot. So our sight distance, we're going to make that equal to our stopping sight distance of 446 feet. So we're going to first compute the value for A, which is our algebraic difference in the geometric grades. So A equals the absolute value of G2 minus G1. When we plug in the numbers, we get a value of 3.5 for A. We're going to assume when we calculate our first L value, we're going to assume that S is less than L. And we're going to check that once we do calculate the value just to see if it is true. So if we use that equation and we fill in the numbers, we get an L value of 323 feet. So we assumed wrong. L is actually less than S. So when that happens, we're going to use the next equation where S is greater than L, and we're going to compute L again using the updated equation there. So when we use that equation, L equals 2S minus 2,158 over A, and we fill in the numbers, we get a L value of 276 feet, which is, again, less than S. So this equation does solve correctly. And that 276 feet is still greater than the L minimum of 150 feet. Note, though, in MoDOT's EPG 230.2.5 states the following: where practical, vertical curves should be at least 300 feet in length. So in this design example, you would probably bump that length of curve up to 300 feet. Next, we're going to compare our results from the previous page with figure 336, design controls for crest vertical curves in an open road conditions. In this chart, we know our design speed, so we can plot that. We know our algebraic difference A, which is 3.5. When we draw that, we go directly down from that intersection point, and it indicates a 276 foot length of crest vertical curve, which is very similar to what we calculated on the previous page. Next, we're going to start talking about sag vertical curves, and this is AASHTO Green Book section 3.4.6.3. At least 4 different criteria for establishing lengths of sag vertical curves are recognized to some extent. These are headlight sight distance, passenger comfort, drainage control, and general appearance. Headlight sight distance is when a vehicle traverses a sag vertical curve at night. The portion of the highway lighted ahead is dependent on the position of the headlights and the direction of the light beam. A headlight height of 2 foot and a 1 degree upward divergence of the light beam from the longitudinal axis of the vehicle is commonly assumed. It is desirable that a sag vertical curve be kept long enough that the light beam distance is approximately the same as the stopping sight distance. The following equations show the relationship between S, sight distance, L, the length of curve, and A, the algebraic difference of grades, using S as the distance between the vehicle and the point where the 1 degree upward angle of the light beam intersects the surface of the roadway. Next, we're going to talk about passenger comfort and sag curves. The effect on passenger comfort of the change in vertical direction is greater on sag than crest vertical curves because of gravitational and centripetal forces are combining rather than opposing forces. Comfort due to change in vertical direction is not easily measured because it is affected appreciably by the vehicle body suspension, vehicle weight, vehicle body weight, tire flexibility, and other factors. Limited attempts at such measurements have led to a broad conclusion that the riding is comfortable on sag vertical curves when the centripetal acceleration does not exceed 1 foot per second squared. The general expression for such criteria is listed above. Next, we're going to talk about drainage control. Drainage affects designs of vertical curves of type 3 where curved sections are used. An approximate criterion for sag vertical curves is the same that is expressed for crest conditions, i.e., a minimum grade of 0.3% should be provided within 50 feet of the level point. This criterion corresponds to K of 167 feet per percent change in grade, which is plotted in the AASHTO Green Book figure 337 as a drainage maximum. The last thing we're going to talk about with sag curves is general appearances. For improved appearance of a sag vertical curves, previous guidance used a rule of thumb for minimum curve length of 30 times the algebraic difference of the grades. On high-type highways, longer curves are appropriate to improve appearance. Like we stated before in the crest curve tools, the rate of vertical curve, K, is the length of curve per percent algebraic difference in intersecting grades, called A. K equals L over the absolute value of A. A equals G2 minus G1. G1 is the grade of the initial tangent in percent. G2 is the final tangent in percent. If you rearrange the equation, you can get the following two equations. L equals K times the absolute value of A, or the absolute value of A equals L over K. From the preceding discussion, it is evident that the design controls for sag vertical curves differ from those for crest, and separate design values are needed. The headlight sight distance appears to be the most logical criterion for general use, and the values determined for stopping sight distances are within the limits recognized in the current practice. The use of this criterion to establish design values for a range of lengths of sag vertical curves is recommended. Table 337, Design Controls for Sag Vertical Curves. The rate of vertical curvature, K, is the length of curve per percent algebraic difference in the intersecting grades. K equals L over A. To the right, you can see the chart from the AASHTO Green Book Table 337. It is to be emphasized that these lengths are minimum values based on a design speed. Longer curves are desired whenever practical, but special attention to drainage should be exercised where values of K in excess of 167 feet per percent change in grade are used. Just like with crest curves, sag curves have a figure 337, design controls for sag vertical curves in an open road condition. Typically, the designer knows the algebraic difference of his curve, and so what you would do is you would plot what your algebraic difference is over to your design speed, and then from your design speed you'll drop straight down to calculate your length of sag vertical curve. Some recommendations for balancing horizontal and vertical alignments include tangent alignments or flat curves at the expense of long or steep grades, and excessive curvature with flat grades is not a good design. Sharp horizontal curves should not be introduced at or near the top of a pronounced crest curve or at near the bottom of a sag curve. Two-lane roads need appropriate passing zones, so providing long tangent sections is recommendable. Both horizontal and vertical alignments should be as flat as possible at intersections to provide adequate sight distance. For divided highways, variations of median width and the use of independent profiles and chains for separate one-way roads are sometimes desirable. In residential areas, alignments should be designed to minimize nuisance to the neighborhood. Roadway aesthetics are important. Design should combine the natural and man-made features of the land to provide a scenic view. Utilize design software 3D view capabilities of your horizontal and vertical alignments during the preliminary plan stage.
When designing grades at intersections,
Now we're going to talk a little bit about ramps. Grade controls for ramps that intersect the crossroads are the same for the intersection. For merging ramps, grades are established by projecting through the roadway profile grade to the ramp edge of pavement for the tangent section of the ramp. For the curve on the ramp, the horizontal alignment and the superelevation must be taken into account while projecting grades and elevations to the baseline of the ramp. The picture on the next slide graphically shows this procedure. In this picture, which is from our Road 2 class, you can see that we have elevations along the main line edge of pavement. We're taking that edge of pavement elevation and we're projecting it down with super elevation down to the ramp baseline. And we utilize that information to calculate a proposed profile for the ramp to baseline.